Hello, I'm Jianhao Jia from Shanghai University of Finance and Economics, and I'm here to present my work on the approximation guarantees of media mechanism in RD space. And this is joint work with Nick Gravin. So first, let's start with a big topic, mechanism design without money. So here are some scenarios in this field. For example, we have stable matching, where we match people together based on their preference, and we have facility location, where we build facility based on the location of agents. We also have voting, scheduling, and etc. So the general setting here is we have some agents and a planner. So the planner's job is to design a mechanism with no payment rule. Here, no payment rule means no money transit is allowed in the mechanism, and the planner needs to collect information from the agents. So what about the agents? The agents have their private information, and they need to report information to the planner. But the key thing to mention here is they can lie about their information to manipulate the outcome. So therefore, the question here for the planner is, how can we design mechanisms that can incentivize honest reporting? So the planner wants the agents to report actual information. Well, to answer this question, let me first introduce a core setting here called social choice. So we have a set A of candidates and N agents as voters. Each agent has his or her preference over the candidate. So the mechanism here aggregates preference information from all the agents and return a winner or winners from the candidate. And what property do you want the mechanism to have? So first, of course, truthfulness. We want agents to never benefit by misreporting their preference. Okay, and then we have onto. Onto means we want each candidate has some probability to win. And we also want non-dictatorialship, which means we don't want any single agent can control the whole outcome. However, those desired properties I mentioned in the previous slides are very hard to achieve in most cases. So in fact, we have this famous impossibility theorem by Gilbert and Satterthwaite in the middle 70s, where they found that any strategy proof onto a deterministic mechanism with more than two alternatives in A is dictatorial. So now we know that it's very hard to find a good mechanism. So what can we do to avoid this bad result? A common approach here people use is to restrict domains for preference. For example, we can use geometric preference, and this will lead us to strategic facility location. And this is the focus in our paper. So what is strategic facility location? So here we have N agents, each with location information L1 to Ln in RD space. So this is private information, so the agents can lie. Then the planner wants to install K facility, F1 to Fk, also in RD space. The cause or preference here of agent I is just his or her distance to the closest facility. And the objective here is to minimize the social cost, which is the sum of the distance from agents to their closest facility. So now what does truthful mean here? So first, agents can lie about their location. They can report whatever PI they want in RD space. And then the mechanism wants to make sure that each agent can minimize their cost by reporting PI equal to Li. So in our paper, we actually study a special case of strategic facility location, which we called single facility location. So here we only need to install one facility, and we set the cost function here to be the Q norm of PI minus F. So you can see when Q equals to 1, this is the Manhattan distance, and when Q equals to 2, this is the Euclidean distance. The important thing to mention here is the preference in single facility location has this very nice property of single peakness, which means if an agent prefers A1 to A2, this is equivalent to say A1 is closer to the agent's location than A2. This property can help us avoid the impossibility results and design very good mechanism. So now the objective becomes minimize the total social cost, which is the sum of Q norm of PR minus F. So now what do we want the good mechanism to have? So first, of course, we want truthfulness, perhaps onto and dictatorial, non-dictatorial, as we mentioned before. Another aspect we want to pay attention to is the approximation ratio, which is the ratio between the social cost given by our mechanism versus the social cost given by the optimal facility, where in the worst case. So do we have such good mechanism with both truthfulness and a good approximation guarantee? In fact, we do. We have this very simple and classic mechanism called coordinate-wise median mechanism. So again, agents can report any location PR in RD space. So how does the mechanism work? So let's say the mechanism returns vector m. Okay, so how do we decide each coordinate mk of m? Let's say for the case coordinate, mk is simply defined as the median of the case coordinate of n players, n agents. In other words, mk is the median of p1k to pnk. So here, let's look at the example. Let's say we have 2 dimensions and we have 5 agents. So because we have 5 agents, first let's look at the case coordinate. So the median is the third one. So here we find this a median of x coordinate. And we can do the same thing for the y coordinate, and we find this median. So if we pick the intersection of these 2 lines, we get our coordinate-wise median. So now we know how the mechanism works. So the first thing we need to check is if this mechanism is truthful. Actually it is, because of the following reason. So first, if we only look at the case coordinate, so we map all the location of the n agents onto the case coordinate. Now we have n agents location on a line, right? So in this case, we know that reporting PIK equals to LIK can minimize distance for agents I in case coordinate. So on the other hand, we know that we decide the case coordinates of m independent from NA as coordinates j. So if we put these 2 things together, we get our truthfulness result. Now we have the truthfulness. Another question to ask is, what about the approximation guarantee of the median mechanism? So to begin, let me introduce you existing results by Mayer in his SAGT19 paper, which is this square root D approximation in L2 RD space. So this means L2 cost in D-dimensional space. Okay. So first we have this basic results from Prakasia and Jianhao Jia in CLEC09 paper, which is the coordinate-wise median mechanism is one approximation in L1 RD space. And then we have the results that embedding L1 cost into L2 cost will cause a distortion of at most square root D. Now we can come to Mayer's proof. So first, let's assume SC1 of M as the social cost of median mechanism under L1 cost, and S2 of M as the social cost of median mechanism under L2 cost. So first, on the one hand, SC1 of M must be larger than or equal to the minimum of L1 of vectors L1 norm versus L2 norm times SC2 of M. Okay. On the other hand, we already know that SC1 of M is equal to opt1, which is optimal social cost under L1 cost. And then opt1 must be smaller than or equal to maximum of a vectors L1 norm versus L2 norm times opt2. So this is the optimal social cost under L2 cost. So now this just concludes the proof. So we get this very simple proof of the square root D approximation. So here are some other known results. So first we have this Prakasia and Jianhao EC09 paper again. So they set the foundation of mechanism design without money, and they show this basic result of our media mechanism being one approximation in both L1RD space and L2R1 space. And in this MOR17 paper, they derived the approximation ratios of media mechanism in R1 space, so on a line, and using a different objective, which is the Q norm of the objective, a Q norm objective. And when time goes to 2023, in this SCW paper, they found that square root 2 is the tight approximation ratio in L2R2 space of our media mechanism. And then they generalized the MOR17 paper result from R1 space to R2 space. So I also like to mention some recent interest in mechanisms with predictions. So what is facility location with machine learning advice or with predictions? So here we have some extra input, which means we feed the location of agents to the machine, and the machine will later return us with its prediction of the optimal facility location P star in RD space. Okay, so this P star is not strategic, but it can be inaccurate. So what do we want the mechanisms with prediction do? So first, when P star is accurate, we want it to perform better than the case when we don't have prediction. And we also want some robustness result, which means when P star is very inaccurate, so we don't want our mechanism with prediction suffer a lot from the extremely bad prediction. So in recent years, here are several works build a mechanism with prediction based on our media mechanism. So for example, we have this EC22 paper, which shows that an easy extension of the media mechanism is optimal for L2R2 space. And we also have two papers here from Europe 24. They apply the square root D approximation we mentioned in the previous slide for coordinates-wise medium as a black box. They use the results directly. So now let's do a quick summary. So what do we know so far? So first, when D is small, for L2 distance, we have when D is equal to 1, we have 1 approximation. When D equals to 2, we have square root 2 approximation. And we know that these are both tight, right? And then when D goes larger, when D goes beyond 2, we only have the upper bound of square root D for L2RD space. And we also know that with prediction field, they have this black box application of the media mechanism. So a very straightforward question here to ask is this square root D or big O of square root D bound still tight when D goes beyond 2 for L2RD space? Right, because square root 2 is tight for R2 space, maybe square root D is tight for RD space. So our first guess is yes. So what we want to do is construct examples of matching lower bound. Well, after several attempts, we believe this is not the correct thing to do. So we turn to ask, what is tight bound? Well, in the end, we find that the tight bound is actually just constant. And we even extend the result for arbitrary LQRD. So we find that constant approximation actually holds for arbitrary LQRD space. So now let's see the detailed results in our paper. So first we build this function UBQ as the upper bound of the approximation guarantee of our median of our coordinates-wise media mechanism in LQRD space. So you can notice that our bound only depends on Q. So our bound actually was for arbitrary dimension D. And the second thing is that UBQ is increasing in Q and the constant never exceeds 3. You can see here Q equals to 1, UBQ is equal to 1, Q equals 2. We have the upper bound 1.55. Well, more precisely, is square root of 6 times square root 3 minus 8. So when Q goes to infinity, we have UBQ equals to 3. On the other hand, we also show that our upper bound is almost tight. So we can find this lower bound LB of Q and D, which is within 1 minus big O of 1 over D factor of our upbound UBQ. For example, when Q is equal to 2, we have our UBQ equal to 1.55. And from previous results, we know that when Q is 2 and D is 2, the lower bound is 1.41 or square root 2. So these two results are very close to each other. Now let's go to the technical part. So first, let's go over some notation I already mentioned before. So first, PI we use as the location of agents, and then F as the optimal location. So here we only use the information that F is fixed. So we fix the location of F, but we do not use the fact that F is optimal. And then M as the median point. So here we fix M and we normalize M to 0. So now let's see how we construct our optimization problem. So first, let's look at the objective function. Here, if we look at the front part, it's the sum of the Q norm of PI minus F. So this is just the social cost given by the optimal location, okay? And the latter part, if we ignore lambda, this is just the sum of Q norm of PI, which is the social cost given by the median point, because we normalize median point to 0. So now, what does the lambda do here? So when objective value is no less than 0, in the end, then the approximation ratio we get is upbounded by 1 over lambda. And the constraint here is just 0 being the median of PI. So here we also define the signature of PI as sigma PI, so which equal to 1 if the J's coordinate of the ith agent is larger than 0, and equal to -1 if it's small equal to 0. So now we can translate the constraint into the math language, which is the sum of sigma PI is equal to 0. So our general plan here to solve the optimization problem is according to the following 3 steps. The first step, we fix sigma of PI. We fix the signature, and we derive the optimal condition. And the second step, we rewrite our objective function given the local condition we derived in step 1. And the last step, we relax the optimization problem and solve it. So first, we have step 1 and 2. Here we fix the signature of a given agent P, a given location P. We define energy here as the sum of Fj to the power of Q, where J is picked by finding where the J's coordinate of P is larger than 0, or as we defined in the previous slide, sigma J of P is equal to 1. And we can get that for optimal P, we can write this inequality. So for the left side, it's the contribution of the location P to the objective value, and the right side is just a function of the energy of P. And here small delta is a function of lambda. So therefore, we can rewrite the math program, the objective function, into the function of energy of P1 to Pm. Another thing we do here is we normalize F, so that the Q norm of F is equal to 1. This helps us have another constraint, which is the energy of PI is in between 0 and 1. So now let's go to the final step, where we relax the optimization problem and solve it. So first, we let xi equal to the energy of PI for simplicity. So you can see here, we can rewrite or relax our objective in the original problem into this function of xi. Okay. And we can also relax our constraint of sigma pi, the sum of sigma pi is equal to 0, into the sum of xi is equal to n over 2. So you can see the relaxed optimization problem have very simple structure, right? And also it has very nice convexity and concavity property. So the last step here is we find lambda such that the objective of the relaxed optimization problem is equal to 0. And this gives us UBQ, the upper bound, is equal to 1 over lambda. On the other hand, we also construct examples of matching lower bound. So we construct this series of examples for each LQRD space. So this lower bound matches the upper bound when d goes to infinity and is within 1 minus a very small factor of the upper bound of UBQ, of the upper bound UBQ. For example, when Q is equal to infinity, we have this instance with two types of agents. The first type is just 1, 1, 1. We also put the optimal facility at the same place. Okay, and for type 2, we put it at the place where only one coordinate is equal to 2. So, for example, here we have 3 points on each axis XYZ. We also put equal number of agents on each point. So, in other words, it's uniformly distributed. We have n over 2 minus a small fraction of agents of type 1, and the rest we put it at type 2 points. So you can check that the coordinates-wise median here is exactly 0, 0, 0. And this example gives us 3 minus 1 over d approximation. So d goes to infinity, we get our 3 approximation. So we also apply our technique to median mechanism with predictions. So remember we mentioned this EC22 paper. So in their paper, they add this C times n copies of points at the prediction P star given by the machine. So this mechanism they propose in their paper is called this CMPC mechanism, or coordinate-wise median mechanism with prediction. So in their mechanism, they just return the median of P1 to Pn as long as the C times n copies of points at the prediction P star. Well, in their paper, they derived the consistency and robustness guarantees as the function of C in L2 R2 space. Well, in our paper, we generalize this result from L2 R2 to L2 and arbitrary RD space. So first, we also derive the consistency and robustness result, and then we show that from this generalization from R2 space to arbitrary RD space, the median mechanism will not suffer a performance loss of more than 11%. Okay, so this means the median mechanism with prediction also perform pretty good in arbitrary RD space. So before I end, I also like to mention some future directions. So first, it's that in the EC22 paper, well, they have this optimality result of the CMP mechanism. Well, they say that the CMP mechanism is optimal in R2 for the trade-off between consistency and robustness. But we do not have this result in our paper for arbitrary RD space. The reason is that we cannot find the characterization of choose for deterministic mechanism in RD space. However, we have this very nice characterization of choose for deterministic mechanism in R2 space. So maybe someone can investigate in the characterization results here first in RD space and then show that the CMP mechanism is optimal, or maybe it isn't. A second direction is maybe you can study as a kind of objectives in RD, for example, sum of squares or equinorm of cos. But one can also study as a mechanism design without many settings with predictions. So for example, the two papers we mentioned before in Neurops 24, in their papers they use this square root D approximation guarantee of median mechanism directly, right? So maybe you can apply our technique and derive a tighter bound of the approximation ratio there. That's all for my speech. Thank you for listening.